right? And as an example, as an introduction, I'm gonna take this example, one that deals with a function that I hope all of you guys are very familiar with, which is the quadratic function, f of x equal x squared. Okay. This quadratic function, when graph, shows a parabola. And suppose you want to find the slope of the tangent line at this point on your parabola, 1, 1. Look, when you graph your parabola, you're gonna get this U shape, right? Opening upward, right? You have seen this in pre-calculus very well, right? But in case you don't remember, as a way to refresh our knowledge, let me pull out our Desmos scientific calculator, the graphing calculator, right? That I talked to you about. We are gonna have this tool, this basic graphing calculator. And in this graphing calculator, if you type y equal x squared, there you see the parabola, right? Now, in case you don't have this access to this graphing calculator, it is in our website, it is in Blackboard. But if you want just the link right now for you to do some graphing while I explain things, here it is. Welcome, Viridiana. We just started with the first lecture. Here is the Desmos graphing calculator, okay? So use this to confirm your knowledge, use this to, whenever you are not sure about the shape of a graph, again, it's a very basic graphing calculator, doesn't give you everything, but gives you a base, like an idea, right? Yeah, so this is the parabola, and I'm paying attention to this part, because I have been asked to figure out the tangent line at this point, 1, 1. Why 1, 1, Professor? Well, because 1 squared, 1 times 1 is 1, right? Yeah, that's it. That's the idea. So 1 here. Okay, great. Now, we graph it here in our calculator. I send you the link, right? Okay, so now, if they ask you to draw a tangent line at this point, right? At this point in green, let's use green here. 1, 1, right? Not hard to do it, right? Somehow, as human beings, we come with a mind that can easily draw a tangent line, right? Like this, right? You know how to do it somehow, right? You just have to share one point locally with the curve, and then you get it, right? Tangent line. So that is not a problem. But the issue is, right? The issue is this. It's easy to do it like this, right? Tangent line, you want a tangent line, Professor? Here it is, the tangent line. There we go, tangent line. Right? Yeah, I did it sort of using my mind, right? Just sharing one point with a curve locally here, I drew a line. But now mathematicians ask themselves, right, is it possible to come up with an algorithm, with a method, with a step-by-step recipe, such that a computer can do what you just did here, right? Computers, they don't have eyes, they don't have this sense of locally sharing one point, right? How can I implement an algorithm to do that? So over years and years, they figured the following out. Said, okay, let's start with something that we are all familiar with, which is the slope of secant lines first, right? And then gradually, we're gonna go somehow from the slope of this secant line to the slope of this tangent line, right? So the idea is this: you start with a point that is not this point, which we're gonna call the base point. This one, this is our base point, right? This point is where you're gonna draw the tangent line. And try to remember this, guys, for your homework 1. A couple of questions there. I'm gonna ask you to figure out the slope of the tangent line following this method that I'm going to explain now. Okay, so mathematicians, right? Let's start with something that we are familiar with, which are secant line and a slope of secant lines. So they suggested, okay, this is your base point. Take a point, call it the point Q here, 1, and draw a secant line. Draw a secant line this way. Secant line here. Draw a secant line there, and this should be your starting point. Your starting point is secant line. All right, there we go. This looks good. Yeah, secant line, right? Secant line. Secant line. And since we're gonna do this several times, let's call it secant 1 line. Secant line 1. Now, there is a way to compute the slope of this secant line, right? The slope of a secant line. How can we compute that, Professor? Well, it's just a matter of figuring out the coordinate here. Let's say this coordinate is, in this case, 1.5, let's say, right? You can take really any point here, as long as it's not your base point, right? In the neighborhood of P, in the neighborhood of P. In this case, I'm choosing points on the right neighborhood of this basic point P, but this can be done also in the left side, choosing points on the left, right? Yeah, 1.5. 1.5, when a square, gives you this value, 2.25, right? Now, Professor, how do you know? Well, I work with numbers, right, guys? I'm a mathematician, so I have these things in my head, but in case you don't, you use this other tool that we're going to use. It's called the Desmos Scientific Calculator. It's in our website. If you want to just grab the link here and put it in the chat. There you go. All right, but it's in our website, it's in black. Yeah, 2.25, right? Yeah, so the input value, the output value. Now, if I have the input value, the output value of the base point, the input value, the output value of this Q1 point, I can compute the slope of secant line 1, right? Secant line 1. How? Well, I take the difference of these two guys, the output values, right? 2.25 minus 1 top, right? Remember the rise, and then over the run, the difference of the input value, 1.5 minus 1, right? Let's write this guy, which is our base point, or better said, the coordinates of our base point in green, so you can remember this when you do your homework. 2.25 minus 1 is going to be just 1.25, right? And 1.5 minus 1, 0.5, right? Now time to do this division. So use your scientific calculator of your choice, or the Desmos scientific calculator that I strongly recommend. Is free, so ER material. The quotient is 2.5, 2.5 here, 2.5. So I successfully got the slope of this secant line, right? The one associated to P base point and Q1, secant line 1. But now the idea is to do this again, but this time now with a point that is closer to P. The idea is to go towards P, to the point P. So I will choose this red point. Okay, so let's draw a second secant line. Let's say this. Okay, great. So this, let's call it secant line 2. And let's call this point Q2, right? Second point. Now, let's say this guy is 1.1. These guys could be any arbitrary point, but what is important is to get closer to P. Let's say this is 1.1. 1.1 is squared, because remember we're working with the square function, right? Square is 1.21. Professor, again, 1.1 is 1.21. How do you know? Well, guys, you don't have to know these things, right? But if needed, use your calculator, right? I'm familiar with these numbers, right? It's 1.21. Very good. Like 11 squared, right? Yeah, so use your calculator, get the point. And now again, right, what is important is that this output value will allow us to compute the slope of this secant line 2 this way. Difference of output values, but sometimes it's called the rise, over difference of input values, right? Which often is called the run. And allow me to write this base point again in green. So you will notice that the base point always goes here, but these guys, they change. Okay, so this difference is clearly equal to 0.21 now divided by 0.1 now, right? But what is this division? Okay, let's do it in our calculator. Scientific calculator of your choice or Desmos scientific calculator. 2.1 now, right? 2.1. 2.1 now. Okay, guys. Now, first question I'm going to ask you is this. We are trying to catch the slope of this tangent line, right? Allow me to write this tangent line in green. So tangent line, right? We're trying to see if following an algorithm, we can end up figuring out the slope of this tangent line, right? Tangent line. And I'm going to ask you guys, where do you think the sequence of numbers is going? Anybody could write in the chat. 2.5, 2.1. Where do you think this is coming down? Just take an educated guess and tell me, right? More or less, right? Anybody? What I see, the students writing. So, Sarah, you made my day. Excellent. Oscar also, Adriana, right? Yeah, it's not like it's obvious, right? But kind of, look, if this is coming down to something, right? And look at the slope here, bigger, less. This is going to 2, right? And if you take another point, let's say 1.01, and you do what I just did here, right? You compute the slope. I bet you're gonna get something like 2.001, something like that, right? But what is important to notice is that these guys that are coming down to 2 is the slope of this tangent line, right? That's the idea. So mathematicians at that moment, they kind of celebrated this because okay, there is a way for a computer to be programmed, right? To figure out the slope of these tangent lines, right? So conclusion here is this. The limit, and this is the first time I'm using this word limit, the limit, right? Important word for us in calculus. The limit of the slopes of this sequence of numbers, right? These slopes of secant lines, right? The slope of the secant lines as Q approaches P, right? So this is a sequence of Q's, right? Approaching P, that's important too. Approach P is the slope of the tangent line. Is the slope of the tangent line. Yeah, so this is how you should kind of introduce yourself the idea of a limit, right? It's a sequence of real numbers that are approaching some other real number, right? I did this from above, from the right? But it's possible to do it also from the left. Indeed, in the homework, you will see that they will ask you to do it from the left, and you will see that kind of you will get to sandwich some real number there in between, and that is supposed to be the limit, right? The limit. So it's sort of informally, right? Informally speaking. All right. So this is just the introduction, right? I will go over one homework problem to explain to you how you have to do this in details, right? But this is the main idea, right? A sequence of values approaching some other value, right? Which is going to be called the limit, and you may say, Professor, can you give us a real world example of a limit in real life, right? Well, I could, for example, give you this example in physics. You know that Albert Einstein determined that in the universe, nothing moves faster than light, right? Nothing moves faster than light. So basically, the speed of light, it acts like a limit for all possible speeds in the universe, right? So if you want to kind of think of that, if that helps, right? Nothing moves faster than the speed of light, right? It's kind of a limit for all possible speeds. Yeah, but then later we will go over this in details. All right, now that was the tangent problem, right? The tangent problem. And then we're gonna dig into this problem